Thermodynamics. Alright, so the first topic that we're going to start up today is going to be thermodynamics, which is finished fluids. Whenever you think of thermo, you think of heat, right? Therm, heat, so we think of that word. Dynamics just means changing. So, for example, it's really cool in here, right? The temperature is pretty nice, but in Savio Hall, how was it? It was hot, right? So, the temperature here and the temperature there are different, which causes what's called a gradient. So dynamics, so thermodynamics is temperature differences, temperature changes, and heat flow. For example, you ever have your computer on your lap and it starts to overheat? And why is it overheating, right? So, I've already my laptop, my old one. We're going to take it apart and look at all the parts to it. You're going to see how it actually works. If you want to come after school, I would need some help. That'd be great. So I'm going to take it apart. We're going to look at things like the fan, the heat sink, actually go through how they work and stuff. We'll do that after school. I want to help you. Or I want you to teach me what you know about it. So that's the major topic we're going to look at. And now, there is a lot, there are whole classes on thermal stuff. For example, I took thermodynamics, I took thermofluid systems, I took heat transfer. Those are 3 classes that I took as an engineer automatically. If I had been a thermal engineer, I would have taken like 10 or 12 more. So again, we're touching the surface like we've always do. Even with fluids, same thing. The next topic after this that we still have to study is looking at vibrations and waves. Okay, so we're going to look at like just general vibrations and the idea of vibrations. Then we're going to go on to waves like sound waves, because sound waves, how do you make sound? You vibrate the vocal cords. You're hearing the vibrations that are vibrating your eardrum, which is then turning it into a sound. That's how you're listening to it right now. I'm sending out a wave that has to vibrate the eardrum in your ear. That's why if you cover your ears, you can barely hear me now. You can still hear me because there's vibrations going on in the room. Okay? That's why if you're under the water and you put your ear on like the bottom of the surface, try it sometime. Go in the pool, put your ear on the actual ground. You'll hear like footsteps of people walking around. That's why people put their ear up to the door when they want to hear something. You're listening to the vibration through the door.
Does the coupling work?
Coupling actually does work, yeah. What it does is it focuses that vibration. It focuses the vibration into your eardrum. It's like taking a funnel and funneling all the sound into one area. That's what the coupling does. So the idea, guys, again, is that we're going to study 2 major topics from this point on. Heat or thermodynamics and heat flow, and then vibrations. When we get to vibrations, we'll look at sound, we'll look at light, all those different things. Because light waves do follow some of the same categories. There are different types of waves, but they do go into that. And that's where it actually leads you into electricity and magnetism. Electricity and magnetism really starts off with stuff like the electromagnetic spectrum, which is light, which is like, Roy G. Biv, or ultraviolet rays. How do you know that you're getting burned by the sun? For example, most people don't realize this, guys. You go to the beach in the summer, or if you're out on a very, sunny day in the summer, even if the clouds come over as overcast, you still get tan. You still get that color. You can still get burned. You want to still remember that you have that on you, so that the whole time you still have, you're covered with the sunscreen. If you're not, unplug that before you do it, just so it's not on the board for you. If you're out in the summer and you still have that cloud coverage, the UV rays do still come through the sunlight, or do still come through the clouds. The sunlight, or the visible spectrum that we see from the sun, that doesn't come through because those water molecules in the clouds are blocking the dirt molecules that are there. But those UV rays, they still come through. So a lot of people get the most burned, or get burnt the most, on days that are actually cloudy. Because they think it's cloudy, they say, I don't need sunblock today, right? It's cloudy out. And that's a lot of the time that people actually end up getting burned, or they end up getting, more color in that time. So we'll go into the beginning of light. Okay, we'll go to the beginning of it, and that leads you into physics 2, which begins really with like optics and lenses. You start looking at lenses and focal points and how they work, and then you start going to like electrical circuits. You go looking at electrical force fields, all that kind of stuff. So physics 2 is a great course. What I chose to do this year and last year, and what most schools do, is teach physics 1 and then physics 2 separately. So for example, if you, they have it next year? I assume so. When other teachers are qualified to teach it, I just have one teaching it. And Mr. Malchik, Mr. Smith, Ms. Jenkins, they all know physics well enough to teach it. Yeah. I mean, she teaches physical science, which is the conceptual idea of physics more than anything. So if you're able to understand the conceptual points of physics, you can really apply it. But she was a science major in college. So she studied all this stuff. Just like engineers are studying all that in science and technology. That's where, it comes into play. Okay? So let's talk about heat for a second. Let's discuss. And misconception number one. You know, we talk about misconceptions like, you know, the sun is further from the Earth is further from the sun in the summer, and it's closer in the winter. It's like the reverse of what you would think. Here's another big misconception, and I want you to just by a show of hands, okay? What is colder? What is colder? This ledge or this part of the desk? Now think about it.
Tell me about this.
Guys, can we follow rules for once? Come on. Really, really disturbing that you can't do that by now. This wooden leg here, this metal ledge. I want to show of hands. There are 3 possible answers. Okay, 3 answers. The metal ledge is colder, the wooden leg is colder, or they're the same. Okay? So, the metal ledge is colder. 10, I see. The wooden leg is colder. They're the same. Okay. All right. Crazy part. They're the same. Yeah. Now, let's discuss how this works. It's really weird because try it. Everybody, touch the leg on your chair right now, the metal part. It probably feels pretty cold, right? And now go ahead and like touch your sweat. It probably feels pretty warm, right? Now, the idea is this. You're not feeling right away the temperature necessarily. You're feeling the conductivity. So for example, this here, you're not feeling that it's colder, but you're feeling that it can take the heat from my hand and absorb it into the metal. So it feels like it's colder. Because the idea with heat is this. There's one simple thing you always have to remember. Whenever you have heat, it always flows from hot to cold. The temperature gradient exists when you have 2 different temperatures and one is hotter than the other. Air, pressure sensors, all that stuff, when you look at weather, when they talk about pressure fronts and cold fronts, air never moves from cold to hot. It's always hot to cold. So your temperature of your hand right now is what, like 98 degrees? That's the body temperature? The temperature of this, yeah, it's only 70 degrees. So you're flowing the temperature or the heat from your hand into the metal. The temperature of this wooden leg is still 70 degrees because this room is in a state of thermal equilibrium. At least that's what we hope for when we have air conditioning, right? Air conditioning is to keep the room at 70 degrees or whatever the temperature setting is. That's where you get that variation or that fluctuation when it turns on and off. So by touching here, it's 70 degrees. I touch here, it's still 70 degrees. But metal is much more conductive than wood is. So all the heat that's in my hand is escaping. Thus it's making my hand feel colder, and it makes the metal feel colder. Here, though, less heat is escaping my hand into the wood. So it doesn't feel like it's as cold. It feels like it's warmer, right? But this wood right here is the exact same temperature as this metal is right here. No difference at all. But you want to say that this is colder, don't you? Because you're touching it. Think about it if you're outside in the winter. You don't want to put your tongue to a telephone pole for many reasons, right? You've seen that on, Christmas stories now. But generally, metal feels colder. It's not actually colder. It's the fact that your heat in your hand is being transferred quicker. The heat flux or the heat gradient is much greater. You're losing heat at a faster rate. Elizabeth and Christian.
The temperature of your hand matters.
Absolutely. The temperature of your hand matters for sure.
What if your hands are like always cold?
If your hands are colder than this metal, the metal feels warm to you. And think about that for a second.
Yeah.
If your hands are really, really cold, even if something else is cold, if it's warmer than you are, it's going to feel warm. It's all about relativity, right? So if I'm standing outside and it's like, 95 degrees out, right? But my body is 98.1 degrees, I'm going to sweat. But theoretically, the outer temperature is still cooler than I am. But when I go to the desert and it's 102 degrees, now the ambient temperature around me is hotter. It's 102 degrees, so it's going to feel even hotter. But if I'm in a situation where, like my body right now is at 98 degrees here, and this room is at 70 degrees, this air around me that I'm feeling, it feels pretty cool, doesn't it? Because constantly, all the heat from my body is flowing. It's flowing out. And that's why in the winter, has anyone ever told you in the winter when you're cold, even if your feet are cold, where do you put? What do you do? What do you put on? You put on something here or something else. Believe it or not, socks is not the best thing that'll help you. A hat is what will help you the most. It's just simply the heat rises. That's the main thing. You have no more pore. Everybody used to, the lesson that people used to say, oh, heat escapes in your head more because there's more pores and stuff. No, that's a load of, that's not true at all. Okay? The idea is that heat rises. So out of all the parts of your body that's going to lose heat, it's going to lose it to the upper part of your, wherever the highest part of your body is, which is not your head. Now your feet are the lowest part of your body, so they're going to feel the coldest. So by putting on a hat, you're actually keeping that heat in your body. So in the winter, if you're cold at home and you put socks on, it doesn't do much for you, throw a winter hat on and wait like 5 minutes and your feet will probably warm up. Okay, it's very weird to think about this stuff. Same thing goes for your body. Like Ever seen Batman, The Dark Knight?
Yes.
Or not The Dark Knight, Batman Begins, the first one?
Yeah.
Okay, there's a scene in there where he's fighting Liam Neeson, when Liam Neeson is training him, the very beginning of the movie. He's in China, and he's already in the jail, and he's working with Liam Neeson, and Liam Neeson is, what's the guy's actual name? Ra's al Ghul. Ra's al Ghul is Liam Neeson, that was a disguise, in the end you find out. So he's training him out on the ice. Remember they're fighting on the ice?
Yeah.
And at one point, Batman or Christian Bale gets Liam Neeson down to the ground and gets him into and he says, something like, he finally gets him down. And Liam Neeson goes, you have to be careful of your surroundings. He hits the ice, and Christian Bale falls to the ice, right? And then you see him trying to warm up. Remember when he's trying to warm up there, and he's sitting there like this? What does Liam Neeson say to him? Does anybody remember? A certain line there.
He said, cover your chest because your legs aren't moving up.
Yes. He says, warm up your, because he's sitting there, Batman or Christian Bale is sitting there going like this to his arms, right? And Liam Neeson says to him, he says, warm up your chest. The rest take care of themselves. Why is that?
The heart.
Okay, the heart is in your chest, and your heart pumps what? Blood, which does carry heat, good. What else? And this is where you have to start thinking about radiation.
Your
What's the term radiation? Okay, spreads out, sure, radiating. For example, if you go home and your parents might have said, turn on the radiator because it's cold in the winter. What is a radiator? It's got that water flowing through it. It puts off that heat, right? A radiation is like a heat source that gives off other heat. So what he's telling Batman is pretty much warm up your chest and your heart in that area, and it will radiate the heat to the rest of your extremities. Let them worry about themselves. You warming this up is great, but you want to warm up your core so that the rest of your body can be warm. Just like the Earth. The Earth's core is very hot, right? It radiates heat to the rest of your surface, to all your different layers of your surface, whatever they may be. All set? Yep. Thank you very much, sir. Appreciate it. So for the idea here of, oops, I don't need that up. Are we still recording? I hope. Did we lose our recording midway through, guys?
We're never recording.
We were recording at one point. Oh, there it is. Yeah, it's still recording. Nice.
Why does it say 12 though? Is that why they say drink something cold if you're cold?
Yeah, well, you don't want to do anything extreme because you can get hypothermia. For example, ever come in, your hands are freezing. Maybe you're playing in the snow, having a snowball fight or something. Your hands are really cold. You don't want to put them under hot water. They go into shock. Put them under hot water. That's gonna burn, right? It hurts a lot. You need to start by putting them in room temperature water to start. You get them to get down to a certain. So, for example, here's my hands. So my hands are at. I'll use the board once it comes back up. My hands. Sorry. Whatever. So let's say your hand is at. Your hand is at. I don't know. Let's say it's at 75 degrees, and we'll use Fahrenheit for now. Okay? And you come inside, you put your hands in 90-degree hot water. Your hands are going to start to feel like they're on fire. What you really want to do is put them in a bath of water that's I don't know, maybe 80, 85 degrees, so that they come up to 85, and then eventually you start to warm them up by rubbing them together, and you can put them under hotter water then. So the idea is the temperature gradient is too much for your body to undergo. So if you're at a really low temperature and you put a really high temperature, you're going to go into shock. Your hands actually can get hurt from that. I don't know too much about shock, but that's the terminology used. Christian.
So, but wouldn't it take longer for metal to heat up, or certain substances to heat up than other substances?
Yes, and that's called a specific heat capacity. We'll talk about that. You learned about that in the physical science and chemistry book. It's that C value, it's joules per kilogram Celsius and stuff. The whole idea is that if you wanted to warm up, or you wanted to boil water, put it on the stove, turn it on, right? It boils after a certain amount of time. But if you have say you have pasta sauce, it's a different consistency, different thickness, it takes more heat to get that to boil. It actually does. So they have different specific heat capacities. It's the same idea as the ocean. But why doesn't the ocean freeze over while lakes do freeze over? There's several reasons, but one of them is one of these. Salt, isn't it good? The salt is doing that. It's constantly moving, which actually increases the temperature. Moving increases your kinetic energy, increasing temperature. The other big thing about the water is the specific heat capacity of water. The specific heat capacity of water is different than, for example, gravel. Ever been outside in the winter or in the summer when it's a really sunny day and say you're playing basketball or say you're barefoot somewhere and it's a black top? What does it feel? It's crazy hot, isn't it? And how long does that take to get hot? Not long at all. You get up in the morning, by 6 o'clock, that surface is going to be blazing hot. Now, you jump in the pool, the pool is not going to be crazy hot, right? It takes a longer time for the pool to heat up. Granted, there's more mass. MC delta T is where I come in with that, when you use that formula. But there's more mass, but then the C value, the specific heat, is also different. So based on the material substance and the material properties, yes, absolutely, Christian. It will take longer or shorter to actually increase the temperature of something. Are we? There we go. Now we're working again. Perfect. Let's go back to our smartboard. Should be working. Hopefully.
He made it worse. Oh, there we go.
No, it was just something else that needed to be fixed. There we go. Now we're back. I saw a hand up in this area.
But I was just gonna ask, why does your hands hurt so long?
When they thaw, why do they hurt?
Because my hands are frozen and it starts to warm up.
I'm not really sure the answer to that. I mean, your hands are gonna hurt because they're cold. You know, I mean, like your skin is cold, you'll feel more sensitive and stuff. Maybe your bones start to get like. Ever hear old people in the winter say like, "Oh, my arthritis is kicking in," you know? In the winter, when it's different temperatures, your joints in your body, like your elbow joint, your shoulder joint, there's different there's ligaments and tendons in there, and the temperature is always a function of it. And as you guys know, temperature changes the the volume, thermal expansion. For example, in the winter, I gave you guys an example with your tires. I know I talked about this, how I use nitrogen. Remember I discussed that? The reason I use nitrogen in my tires is because in the winter, the nitrogen molecules do not collapse on each other. They don't actually get closer like oxygen molecules do. Oxygen molecules have a tendency to get closer when it's colder weather, like most things do. So your tires seem to look like they're flat in the winter. You can add more oxygen. And in the summer, they're always filled. They're always completely filled, unless you have flat, obviously. Because the idea that the oxygen gas that's in your tire in the cold weather comes closer, compresses. And in the hot weather, it expands, just like a hot air balloon. Okay, the hotter it is, the more it's going to want to expand. The only exception of this we've discussed is water, H2O, because of the hydrogen bond. That's the reason why. The hydrogen bond is what causes that. So if you think about it, when we talked about putting ice in the freezer, you fill the ice jar with water, you throw it in the freezer. Doesn't it expand actually? And it's getting colder, which doesn't make sense. Normally when things get colder, they contract. They get smaller. The molecules become more aligned. Okay? So there are exceptions to thermal expansion, and when we talk about it today, we're going to make sure that we emphasize the fact that there are exceptions to thermal expansion.
So, Mr. House, so is it better to fill your ice tray up with hot water?
No. That has no effect. The idea is that what would if you fill the ice tray with hot water, it would have to get colder first, and then it would have to freeze. So you have to actually take more energy to do it.
Because some people like to use hot water and freeze it quicker.
Freezes quicker? No, it actually freezes longer for sure. 100% sure. Phase changes. It's all about phase changes. And we're going to talk about phase changes. We're going to look at solid, to liquid, and gas. And then we have like latent heat and stuff, how you break those bonds, and that's the reason. But we'll get into more detail, but yes, colder, better. All right, let's just start by discussing the idea of temperature. So let's start with temperature. Okay, let's start with temperature. Now this is one question that I want you guys to memorize forever. I really do. And a lot of people don't know this, and there's a very simple way to define temperature. Who remembers maybe from physical science? Who'd you have again? Mr. Miles. Okay, so he definitely would have gone over this. All right. What is the actual definition, though, of temperature? What is it, Karen? Very good. It's the average kinetic energy. That's all it is. Okay, temperature, and then we can say of the molecules. But it's the average kinetic energy of the molecules. Okay? If you remember average kinetic energy, that's fine. And why I say average is because the temperature on the surface of my skin is different than the temperature of my heart, right? We're going to be two different temperatures based on where they are. So I'm just using average because everything has different temperature gradients. Even if something, like this table is probably like 70 degrees across the whole thing, but there's some fluctuation probably, right? Somewhere. Maybe this is like 70.001, 70.002, 70.00001. There's definitely fluctuation. So there's never going to be the same temperature of all things. So if you want to find the temperature of this table, it's the average kinetic energy of the molecules. Now, kinetic means what?
Motion.
Motion. Very good, motion. So really, if something has any temperature, it has motion. But this desk isn't moving, but it has a temperature, doesn't it? If I were to actually measure it, it'd have a certain temperature. It's vibrating. On a molecular level, it's actually moving.
But if you, have you ever when you go like this,
Mhm.
like even if your hands are like Cold,
Mhm.
cool your hands, what is that?
You're increasing the kinetic energy, thus increasing the temperature. Absolutely. Why? That's why you do that, guys. I mean, there's other reasons, obviously. When you do this, you create what? Friction, which creates heat. Friction, in the form of friction, is heat. You gain heat. But why do you gain heat? You're increasing motion. Motion is increasing. Kinetic energy is increasing. Thus, temperature is also increasing. Okay, so remember that temperature is really the kinetic energy of the molecules. So, the whole idea for a long time was this. How close can we get to no motion? How close can we get to no motion, or the absence of any motion? A solid, sure, but solids, again, this desk still has temperature, doesn't it? Remember? And it's a solid. So there still is some motion there. So that's where the whole idea of Kelvin came about. Good. Kelvin was that absolute scale. The absolute scale going down to 0.
Motion. Or for example, I was gonna say, talk about plate. Like, you turn on the flashlight, actually, and put it in the hole inside the wall, it's moving so fast.
Theoretically, sure, but the idea there is that the mass of the photons is so little, and it's E equals mc squared. The mass is so little of a photon that even though it's traveling at a high speed c, the energy that's coming out is not going to be a lot. Now, if you magnify it like a magnifying glass, you're magnifying all those photons onto a concentrated point. That's where you ever go outside with a magnifying glass trying to burn something before?
Yeah, we didn't know.
Okay? You could try it sometime. Grab a magnifying glass. Be careful, obviously, because it's going to actually burn. Take a piece of paper, a magnifying glass, put it up to the window, and keep moving the magnifying glass until that light that you see on the paper focuses on like a little focal point, and hold it there for like a minute. It'll start to actually smoke, and it'll start to burn. The paper will actually start to burn. Because you're taking a photon and you're concentrating it. Now, yeah, enough of those? Sure. And that's where lasers come in. You take a laser that could burn a hole through the wall, that's what they're doing. They're concentrating all that energy. So it's different. I mean, I don't know if that answers your question completely, but that's the general idea, without going into a lot more detail. What I want to do though, real quick, is discuss the idea of zero temperature. And this is what confuses many people. And it's a very easy topic once you explain it in a certain way. So, let's say, for example, I've got a can of soda. Okay? I've got a can of soda, and it's at room temperature. But I want to drink a cold can of soda, what do? Put it in the refrigerator, right? Why do I put it in the refrigerator?
Put it in the freezer.
Why do I put it in the refrigerator, people?
Cool down.
To cool it down, right? So let's look at a scenario here. Can of soda at room temperature. We'll say room temperature is 70 degrees Fahrenheit. Okay, let's say that. Can of soda at 70 degrees Fahrenheit. Gentlemen, come on. What do we talk about? Focus this way, else we'll put them away. The can of soda is at 70 degrees Fahrenheit. Now, I want to get it down to, let's say, 50 degrees Fahrenheit. 33 is freezing, or 32 in this case, sorry, is freezing. So I'm not going to get it too low that it will freeze. I want to get it to 50. If I want to get it down to 50 degrees Fahrenheit, I have to put it in the refrigerator, right? So now it's inside of the refrigerator, and I want it to get to 50. For it to get to 50, what do I have to know about the refrigerator itself?
The temperature of it?
Yeah. What does it have to be?
30.
Okay, 30. Where's 30 coming from?
Average? Yeah.
Okay, you're adding the average, good. Theoretically, though, if I put this in the fridge, and the fridge's temperature was 50, if I let it sitting there for 2 weeks, it'll get to 50 eventually, right? Because if the interior temperature of the fridge is 50, and I put something else in there that's 70, eventually it'll get down to 50, but it'll take longer. But if I pick the fridge at like 30, then it'll go a lot faster. And that was, if you remember from last year, Newton's law of cooling in Algebra 2. Newton's law of cooling was the idea that you put you boil a pot of pasta, how long does it take for it to cool off? You can figure that out based on the ambient temperature or the temperature around you. So if I want to get this down to like freezing, I have to put it in the freezer, right? And the freezer is like 15 degrees Fahrenheit, so that it'll get it down to 32 degrees Fahrenheit, so it'll actually freeze. Now, what if I want to get it down to no temperature at all? So, and if we know about this, 50 degrees Fahrenheit has some motion of the molecules, 30 has less motion, then it becomes frozen, there still is motion. But if I want to get it down to no temperature or no motion at all,
0 Kelvin.
I want to get it down to 0 Kelvin, that's that scale that they call it. Now, in Fahrenheit, there's a scale called Rankine that does the same thing. Okay, it's called Rankine. I'm just going to discuss Kelvin for now, because some of you are familiar with it. So, if I wanted to get something down to, that was our starting point. If I wanted to get something down to, come on. There we go. Why is our smart board not working? All right. So, if I wanted to get something down to freezing, or 32 degrees Fahrenheit, that's really 0 degrees Celsius. Okay, Okay, that's what 0 degrees Celsius is. That's where the corresponding comes in. We'll talk about formulas about this next class, but just generally speaking now. So, if I want to get something to be frozen, I need to get it to 0 Celsius. The lowest possible temperature, it turns out, just so you know, 0 degrees Celsius is really 273.15 kelvins. Okay, kelvins. And what kelvins are the idea that you can't get lower than 0 Kelvin. There's no such thing as a negative Kelvin. Kelvin is the absolute temperature scale. So when you get down to negative 273.15 degrees Celsius, that's what 0 kelvins is. That's the lowest temperature possible. Remember in the winter, ever go in the winter and they're like, oh, it's really cold out today. With the wind chill, it's negative 10 degrees. How could you have a negative temperature? It just means that it's getting lower and lower and lower. But theoretically, the lowest temperature possible is like 0. Well, that's on the Kelvin scale. For something to get down to 0 Kelvin, you would have to put it in a refrigerator, right? A really good refrigerator, obviously. What would the temperature of the refrigerator have to be for it to get down to 0 Kelvin? It would have to be 0 or like really something less than 0, right? Theoretically, to get it to get cooler. So like maybe like negative 0.11111 or 0.001. So in order to cool something down to 0 Kelvin, you need something colder than 0 Kelvin. But 0 Kelvin is the limit. You cannot get anything colder than that. So this is the weird part. You can never really get here because you need a refrigerator colder than this. But you can't get anything colder than this. So by like the law of syllogism, if you remember from geometry, or the chain rule here. If you can't get something colder than this to cool it down, you can never actually get here. So scientists for a long time have tried to cool stuff down to 0 Kelvin. They can't get there because to get to 0 Kelvin, they would need something colder than 0 Kelvin. So the idea is like a computer, for example. People, what they do is called overclocking a computer, and we'll talk more about this later, but it's the idea that you supercool your computer so that it runs really fast. The hotter your computer, the slower it runs, by the way, by default. The hotter it is, the slower it runs. The colder it is, the faster it runs. Now, there's obviously a limiting factor. If you completely freeze it over in this frost on, it's not going to work. But you want to run like coolant, like nitrogen, or liquid form of, like for example, hydrogen over your actual CPU, your central processing unit, which provides the most heat or gives off the most heat. So you cool it down. So you run hydrogen over it and it cools it down. Well, if I want to cool something down to this temperature, I would need something colder than it. But it's not possible. This is the lowest temperature. So if I can't invent a refrigerator that's less than this temperature, I can't actually even get to this temperature. So scientists have gotten to like decimals or 0.001 kelvins because they're able to get so close to absolute 0. But the idea of absolute 0 is really the idea of having no motion whatsoever. But every single thing around you has motion on the molecular level. And that's why in the beginning of the year, if you remember, I think it was Kenny that used his smart aleck remark when I said, like, am I moving right now? And he said, yes. But really, on a macro level, am I moving right now? I'm standing still, right? I mean, my mouth is not moving, obviously, but if I stand here, I'm standing still. But even your desk right now, it's moving at a micro level or at a nano level because the molecules are really vibrating right now. And that's where next chapter we're going to tie this into vibrations. Vibrations are forms of energy. So sure, everything is moving. So the idea of absolute 0, I want you to remember, is that you can never get to absolute 0. Because to get to absolute 0, you would need something colder than that to cool it off. If I want to get if I have a, say, ever put a cup in the freezer? Yeah. People put glass in the freezer, like frost a mug over, and then they'll put like soda in it, and it gets the soda really cold because it's putting it in a container that's colder than it. That's what it's doing. Well, I can't get anything colder than this. So how can I ever get to this temperature if there's nothing colder than it to cool it off? It'd be like having an air conditioner that was running at negative kelvins to get it down to 0 Kelvin. Well, you can't have negative kelvins. This is the limit. So by default, you can't actually ever get there. Mark?
Doesn't glass breathe?
Yeah, that's what I'm saying.
Oh, absolutely. And there's certain things that if you go down too cold, they'll become brittle and they'll actually start to break. Absolutely. If you put something in that's too cold, eventually it might shatter. Yeah. And different materials have different properties. So, for example, something like hydrogen, that's in its natural form, it is a gas. Hydrogen in its normal form is a gas. We see it, around us. It's all around us. Actually, you can't see it, but it is. In other forms, you can contract it down to a liquid. You can try and get it down to like an actual solid. I mean, it's not, easy to do. You have to really cool things off for it to work. So that also goes back into specific heat. Well, it comes back to that as well. Another hand was up over here.
Well, basically, when they give the definition for cold, it's basically like the opposite of heat. So wouldn't it basically, like, since you're putting it in a container, or something, you're just putting it in the fridge, wouldn't it therefore, like,
But the thing is this, if you want to remove all the heat from it, you need to get it down to 0 Kelvin.
right.
To get something down to 0 Kelvin, the surrounding has to be less than 0 Kelvin. That's the idea. A refrigerator works because its temperature is less than the object you're putting in. Think about it logically. A refrigerator works because its temperature currently inside of it is less than whatever you're putting in. That's what cools it off. How do I get something less than this if this is the limit? To get to 0 Kelvin, I would need something colder than 0 Kelvin to cool it down. But I can't have something colder than 0 Kelvin because this is the lowest temperature possible. So by default, I actually can't ever get here. This is a limit. So the idea is this. You have an asymptotic graph. Why is this smartboard not working today? If I want, I'll do it on the regular board then for now. I don't understand why the smartboard's acting up. Real quick before you guys go, just think about this. The temperature of something can get down further. This is a Kelvin scale. This is the amount, like, over time. The temperature will get colder and colder in a fridge, but it will never reach 0 Kelvin. It will become asymptotic. There is a horizontal asymptote there. It will never cross this boundary because this is 0 Kelvin. Okay, James?
You know how some fridges where you put the vegetable over there has the humidity control at the same temperature?
Humidity control?
Yeah.
Humidity control is having moisture. It's going to change that. The temperature control is usually a different one. I think there's a temperature control like 1 to 9 and humidity control after.
Yeah.
It might have something to do with it, yeah, especially with vegetable stuff, you want to keep it moist. So that might have that. Tomorrow we'll get into more of this stuff. Today was more of an intro, guys. So yes, no homework tonight or anything. Again, make up for your test. I want to see you after school here.
Wait.
Now it's working? Yeah.